Hey, welcome back to Math with Patrick. Today is July 22nd, and we're solving problem number 203 from the Daily Epsilon calendar. Of the 64 ways to flip a coin 6 times, how many have more heads than tails? So I think first let's confirm that the 64 actually is correct. So if you flip a coin once, you're going to have two options. It's either heads or tails. Not much there. If you flip two coins, or one coin two times, we could get heads and then another heads. We could get heads then tails, tails then heads, or tails then tails. There are four options here. With three coins or the same coin three times in a row, there are 8 options. Essentially, it's going to be these options right here followed up by heads, or those options again followed up by tails. So just to write it all out, we could get all 3 heads in a row. We could do heads, tails, heads, tails, heads, heads, or tails, tails, heads. Basically, I took all 4 of these and just put an H at the end. Or we could get heads, heads, tails, heads, tails, 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 heads, tails, or all tails. And this method of essentially just copying what you had before and then doubling it will hold true for this entire sequence. So we could just take this bottom number and double it all the way up. So with 4 coins, we have 16 outcomes, 5 coins, 32. And then finally with 6 coins, we do have 64 outcomes. Kind of interestingly, if you follow this pattern backward and you have 0 coins, then you actually have one option. Because if we if we multiply by 2 to go right, we'll divide by 2 to go left. And so 1 is the number that makes the most sense here. So interestingly, in a lot of counting problems, the null event does actually count. We aren't flipping any coins, but kind of the math says that that is the one valid option. With no coins, you get nothing. That's your one option. Anyways, with our 6 coins and our 64 options, we need to figure out how many have more heads than tails. And we can kind of get a good sense of the different options here. Basically, we could just kind of figure out of the 6 coins, how many heads do you have? And we want more heads than tails, and so 3 heads is not enough. That's not more than half, that is only half. So we are going to count the options where we have 4 heads. We're going to count the options where we have all 5. And then we're going to count the options where we have all 6 being heads. And actually, this one over here, where all of them are heads, this is the only one time that it could happen. Right? Because to get 6 heads, you need each individual coin to come up heads. And so there isn't much wiggle room with that. Oh, I also just realized that this H right here should have been a T. So this scenario of 6 heads only shows up once, and that's if you happen to flip 6 heads in a row. For 5 heads, we do have a little bit of wiggle room here, because maybe the first coin showed up tails, and then the rest of them showed up heads. Maybe the second coin was the one that was tails, or the third, or the fourth, or the fifth, or the sixth. Essentially, of these 6 spots, we're just going to choose one of the 6 to be where the tails shows up. And that shows us that we have 6 options here. And then for 4 heads, oh wait, hold on. This feels kind of small. The answer is 22, right? So I guess I'm going to get whatever 22 minus 7 is right now. So I guess there's going to be 15 here. Let's hope so. So how many times could we get 4 heads and 2 tails out of flipping these coins? We could just try to count it, and that might not be too hard. There are more advanced methods that I will talk about real shortly, but I want to just think about it as concretely and as logically as possible first. So I'm going to think about how many different ways could I put 2 tails somewhere in this stack of 6 coins. Well, it makes sense to me to try putting them first and second. I get my 2 tails first, and then all the rest are heads. And then I could move the other tail to any of these other spots right here. And all of these are just different scenarios of when those two tails show up. So of the scenarios where the first coin is tails, I have 5 other scenarios to count, or 5 total scenarios to count, right? 1, 2, 3, 4, 5. All of those are distinct outcomes where we get 2 tails, but they just show up in different spots. Then we could think about the times when we get tails in the second spot. And I want to make sure that I'm not going to double count this one again, because I already accounted for that scenario of getting tails, then tails next. And so I'm going to only count all of these ones as the other scenarios where I could put those 2 tail tosses. Essentially, there's going to be 4 different spots, because this one I'm assuming is already there. And then we have 1, 2, 3, 4 different other spots where the other tails could show up. And we can kind of continue this pattern where now I'll make that one a tail here, and then I have 1, 2, 3 other options for kind of that leeway of where that second coin goes. And maybe you're going to see what this pattern is doing now, where at this point I'll have 2. And then once I decide that I haven't seen any tails yet, but I do see my first tail on coin flip number 5, and I'm assuming that I have 2 tails or 4 heads, then I need the other one to go right here. And there was just the one option for that. So overall, if I add up all these numbers, this right here is 10, plus 5 is 15. I do get that 15 that I want. So all of these scenarios, these 15 plus the 6 plus the 1 scenario, do make the 22 that we were looking for today. To kind of generalize this, I actually want to show you Pascal's triangle before we finish the video. Pascal's triangle starts out as just like a little number puzzle where you start with a triangle of ones and you kind of expand them going downward. And so the first row has 1 number, then we have 2 numbers, and so the third row is going to have 3 numbers. And to produce these numbers, you just add the 2 numbers from above. And so the 1 plus 1 makes it 2. And then kind of since this number doesn't have a number to the left, it only has this 1. That's kind of why, at least my justification of why I want to call it a 1, because it's kind of like 0 plus 1 in a sense. And we could just continue this pattern of 1s along the outside, and then to produce these middle numbers, we'll just add the 2 numbers above it. And you could keep going essentially infinitely here. And this triangle just keeps growing. And this is just called Pascal's triangle. And it shows up a lot in these counting problems, especially when you're the one kind of choosing how many of the events you want to have a certain outcome and how many of the events have another outcome. So like exactly what we were doing with the coin toss. And maybe you just noticed that the 15, the 6, and the 1 do show up perfectly right here in Pascal's triangle. And anytime you're doing these counting problems where you have a set amount of things, they could go one way or the other, and it doesn't really matter like that this one was a tails first before that one. Like we could swap these 2 coins and that would be kind of the same scenario. Essentially, we're doing something called the choose function. Anyways, I'm kind of giving you leads if you wanted to explore this more, but I'm not going to go too far into it, at least for today. I at least wanted to show Pascal's triangle. You can think of this 15 as showing us how many different ways we could get to that 15 by starting at this 1 and either choosing left or right as our direction. In fact, any of these numbers, as you go across Pascal's triangle, represents the number of ways you can approach this number. Like to get to this 1, where our only instructions are go left or go right, we have to only choose lefts. There is just one option to get to right here, and that's choosing a whole bunch of lefts. But to get to this 3, we could go left, right, right. We could go right, left, right, or we could go right, right, left. And so once we know that it takes, or there are 3 routes that lead to this 3 and 1 route that lead to this 1, then it would make sense that we would add the number of routes to get to this 4, or we would add the 3 and the 1, the number of routes to get to the above numbers, to get the number of routes to get to the number below the 2, if that makes sense. Sorry, that was a little bit wordy. But essentially, once we got down to here, there were 10 routes to get to this 10 of various lefts and rights. There were 5 routes to get to this 5, and ultimately, those are the numbers that you have to stop at right before getting to this 15. And we could just kind of write out one of those examples. Like we could do right, right, left, left, right, right. And so I could have something that looks like RR, LL, RR. And these two L's could have been kind of anywhere within the sequence, right? We could have done like L, R, L, and then a whole bunch of R's. And that would have looked like left, right, left, right, right, right. And we end up at that 15. And hopefully these things look really similar to before, because essentially it's just me organizing H's and T's for flipping the coin, or L's and R's for left and right instructions. So if we were asked a different question today, maybe we had 7 coins or 8 coins. Maybe we wanted to know how many have equal heads or more. Then we could just use Pascal's triangle and just figure out more numbers in the triangle. Like for example, if the question said, how many have the same amount of heads as tails or more heads, all I'd really have to do is include this 20 right here within my sum. So instead of getting 22 for today, I would have gotten 42 instead. Or if you wanted to ask like something about this number right here, this 21, we could say 7 coins, right? Because this was our 6 coin row, so this should be our 7 coin row. And then 21 is the number of ways that we could get exactly 3 tails or exactly 3 heads out of 7 coins. So just in summary, Pascal's triangle is a nice generalization to this kind of problem so that you don't have to like actually count out all 15 options and then all 6 options and then add them all up in the end. So anyways, I think I'm all done chatting about Pascal's triangle and coin tosses and whatnot. But feel free to look more up about choose functions, about Pascal's triangle, or essentially just probability and counting problems if you want. But hey, answer's 22. I should stop talking, and I'll see you tomorrow. Bye.